Hello, this is Mike at GameFromScratch, and welcome back to our ongoing SFML tutorial series. Today we're going to be looking at Sprite, which is basically a texture drawn on screen. There's more to the semantics than that by quite a bit, but we'll cover what those actual details are in a second. Again, this tutorial series, there's a whole bunch of them. I'm going to be putting up a link to the table of contents very soon, but I've assumed you've either viewed or watched the previous ones where you already know the topics covered before moving on to the next one. So if I cover something that doesn't make sense to you, I've probably covered it in the past. If I haven't, let me know and I'll make sure that I cover it going forward. As always, there's a text-based version of this tutorial available as well, so don't worry too much about the code. You can go to GameFromScratch.com and get it and follow along. I'll also be posting the GitHub once I'm a bit further along, so you can actually just copy and paste the code in at your leisure. Look for the link down below for the blog post for this equivalence, and you should be able to run from there. They cover basically the same thing, so if you like video, you can watch this. If you like text, you can watch that. Or if you like video and you want to cut and paste the code, you got you covered. So again, what we're covering today is Sprites. Now, in the ancient history, Sprite used to actually mean something special. When you dealt with old 8-bit computers, just like the Commodore 64, the Atari 800XL, etc., or even the early consoles like the Nintendo, you had dedicated hardware for something called a sprite. So one of the features you would hear, sort of like how we have, number of CUDA cores or whatever for our GPUs, back then you used to have the number of sprites. And the hardware would support, so I believe the original, say Atari, supported 4 hardware sprites. And that is, it actually had chips to handle 4 sprites, and a sprite was basically an image that moved. So it was part of your background that wasn't static. It wasn't the world itself on a single screen application, or so. It was like the player, or the enemies, or missiles, or whatever. Like the things that moved around on the screen, those were specifically sprites, and there was hardware specifically for dealing with them and moving them around. So that's where the terminology sprite came from. Now it basically just applies to any graphic with motion. And in SFML terms, a sprite is inherited from drawable and transformable. So really that's quite clearly what a sprite used to be. It's something that can be moved and something that can be drawn. Now the important thing to realize, though, the source of a sprite is a texture. A texture is the actual image a sprite is going to draw on the screen. And that relationship is very important to understand. The texture holds the pixel data, it can load the image from file and all that stuff, but it's a heavyweight class. So say your texture is 2 megs in size, your texture file is 2 megs in size. Your texture is going to have that information in memory, and often you're going to be substantially more memory than your image source, actually, because your image source will have been compressed. So, for example, a 640 by 480 32-bit per pixel, which is the normal, that's red, green, blue, and alpha channel, so 4 bytes per pixel is, well, I don't even want to try to do math, but we're looking at 640 times 480 times 4. So you're looking at like 1.2 million bytes of memory being used for that image uncompressed. And generally when we're dealing with games, we're actually talking uncompressed. So a file that's 640 by 480 with 32-bit color is generally going to be 60, 70, 80K in size on the disk because it's compressed. Now, when it's actually decompressed into memory, it's going to be substantially larger. And that kind of segues nicely into a point we're going to talk about. That's where images formats come in. BMP is the granddaddy of the images. It's about as simple as it gets. More or less, they've just dumped all 4 values to memory, off you go, and they're stored in a linear format. There's very little compression going on there, but as a result you don't get much artifacting or changes to it, so a bitmap file will be quite large. Now on the other hand, you've got, let's say, like a PNG file, a GIF file, or a JPEG file. Those are all compressed in some way, shape, or form, and what they do, they use algorithms. A lot of times it's run length encoding, so they look at, you've got an image typically will have, say, 95 black pixels in a row. It'll just say, instead of going 95 00255, 00255, 00255 byte kind of alignments, it just says, all right, 00255 times 100. So then you just saved, 100 byte, or 100 times 4 bytes worth of space for encoding that way. So that's a very, very trivial kind of encoding that happens, but it does definitely happen behind the scenes. And when you're extracted out to memory, all of that goes away. You're dealing with full-size images. So think about the size of the disk versus the size of memory are completely unrelated points. However, all that covered, I just wanted to impose on you that the texture class itself holds all that memory in an uncompressed form. So not only does it load these things in, it stores that information, whereas the sprite just uses a reference to it. So textures, heavyweight, load them up front, be concerned about how you create them. A sprite, much lighter weight, but you do have to be careful there that your sprite does not outlive its source texture, or it will draw a blank thing to the screen. A very common bug you'll see, or you can encounter when dealing with SFML. So you want to make sure that your life cycle matches up there. Okay, a little bit of back history out of the way. Let's move on to some actual code. As you can see in front of you, here's our very standard boilerplate application. Let me just turn presentation mode on so you can follow along. And we'll jack this puppy up to 150%. So hopefully that's legible. We've covered all this before. This is a very generic SFML application. And now what we're going to do is go ahead and draw a texture. Now, when I run this, it's actually going to error out. It's going to tell me the DLLs are not found and then the image is not found. And that's for a reason. I'm going to show you how to configure both of those things in Visual C++. If you're working with another IDE, sorry, the process is going to be a little bit different. But as long as you're using Visual C++, this is kind of a tripping point for a lot of people. So I'm going to stop and cover how to configure those two things in a moment. But let's just go ahead and create our code first. So as I was mentioning, a sprite uses a texture. So we need a texture first off to load an image from file. I'm just going to use this image right here. It's extracted from an image that was part of the Humble Indie Bundle from a few weeks back. It's just a dragon sprite. Now you can use whatever image you want, as long as it's in the right file format. And let's touch on that for a second. The proper file formats, let me just check from the blog post so I get this right, because a couple of these are a little esoteric. Let me see. Okay, I'm doing it from memory because I don't see where they are right now. Come on. Dun, 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 dun. I swore I wrote this in the post. There we go. So the file formats are BMP, HDR, GIF or GIF or whatever the heck we're supposed to call it these days, JPEG, PNG, PIC, PSD, and Target. Now to go through those formats as I'm aware of them, HDR I'm kind of unaware of. I'm assuming it has something to do with actual HDR, high dynamic range or something to that effect. I forget exactly. It's from it's for using multiple images to make a single composite image, but I'm not 100% positive. It's not a format I use. BMP we touched on earlier. It's a kind of an uncompressed daddy of all formats. Simple but huge. No transparency support. JPEG. I would actually probably recommend staying away from JPEG, but JPEG is a compressed format. Some of the containers support transparencies, most do not. It will give you a small file size, but you will get a lot of artifacting in it. GIF, stay the hell away from. There's absolutely no good reason to use GIF for anything ever again. It's a patent-encumbered format. It's not particularly amazing at quality or encoding. The biggest thing GIF's still around for is because you can make animated GIFs. For a game, no reason at all to use GIF. Screw GIF, stay away from GIF. It's a patent encumbered trap, so don't use GIF. You do have PNG though. PNG is probably what my default choice would be. It's a nice compromise between file size, ultimate quality, it supports transparency, it supports 4 bytes per color, etc. You have PIC, no idea, never used it. PSD, which is Photoshop's format. They're really heavyweight, but a lot of times your artists may actually work directly in Photoshop, so it's handy to support it, but do not ever ship a game using PSD, way too big. And then finally, Targa. TGA, not really sure why you'd use TGA this day and age. It's a pretty old format. I don't remember the upsides and downsides. I do believe it supports transparencies. I don't know why you would pick it over PNG. I know it used to be very popular for high quality but encoded images, but I I don't know why I would recommend it. I would probably stay away from it now, just for the general lack of tooling available around here, Targa, these days. So those are your supported input. For the most part, just use PNG unless you've got another reason, in my humble opinion, especially if you want to have sprite transparency going on. Now, all right, now back to coding. So we need to have a source image. I have that one we talked about right here. It's called dragonbig.png, and we're just going to go ahead and load it. So SF, and then it's a texture, like so. And then we want to go texture.load from, and you'll see here there are 4 types: file, image, memory, and stream. We're going to talk about image in a little bit. Ignore that one for now. Memory and stream are 2 slightly different things. One allows you to load from like an IO stream. The other one allows you to basically load from a big chunk of direct memory. What we're going to do here is load it from file. So here we just pass in a path, easy enough. And I'm going to make it relative path to our working directory. We'll cover that in a moment. So I'm going to create a folder called images, and it was called dragonbig.png, like so. Obviously you swap this in to use whatever file name you're going to be using, but notice the root of my path, and then we're in a subdirectory called images, and we're going to set that up in a few moments, but just continue on. So now sf : okay, sprite. So the sprite is the thing that has the position on screen and can be drawn by the render window, but it ultimately needs a texture to be of any value whatsoever. So we're going to create our sprite. In our constructor, we're just going to pass in the texture we want to use, like so. Now we can use a portion of a texture. We're going to actually cover that in the next tutorial. We can use sprite sheets that have multiple textures on a single, texture on a single texture. We'll look at that a little bit later, so ignore that for now. So we're just going to use the entire thing right here, passed in this way. So we've created our sprite, we've loaded our texture, and then finally, and if you followed the last tutorial about displaying procedural graphics, you're going to find this remarkably consistent. Render window.draw and our sprite. Done. That's it. And now this code will not work in any which way, shape, or form, but I'm going to press F5 and run it so we can blow up. And I'm going to show you a couple things here. First off, it didn't find any of the DLLs. And way back at the first, I showed you how you could set these things up by basically copying the DLLs into your directory. I'm going to show you another way you can go about doing it. For this project, I'm actually creating 2 versions. The one that I work with, that I'm ultimately going to publish to GitHub when I'm finished, and then a throwaway one that I'm creating as I'm doing this video that you can see in front of you. It's right now, SFML YouTube 9021010, yeah. Is the name of our current project, and this guy is going to be thrown away later on. So each time I run this up, I'm setting up a new configuration every time. And what I've done, let me just bring in a folder from off screen here, is I've got, in my temp folder, I have a version of SFML, and each time I create a new project, I'm just linking over to it. And I'm going to show you how to link in the DLLs so that they're pathed in, so you don't have to keep doing this every time. And I'm also going to show you how to set up the working directory. And this is critical so that when we do code like this, the working directory says, okay, our root, so basically the equivalent of, dot or /, is this working directory. And I'm going to now show you how to set up both of those things, at least on Visual Studios on Windows. So just come on into your properties of your project. And what you want to do is go into debugging here. So again, you would have had to have already come in here to set up your header files and libraries and library paths. Now what we're just going to do is a couple more things, but they're all under the debugging settings. And again, remember, this is going to be for debug configuration only. So when you do release, you're going to have to set up a whole new set of these for the release. It takes seconds, so don't be overly concerned about it. But now what we want to do, first off, let's set up the working directory. Right now you can set it set to the project directory. This is going to be in Visual Studio anyways, where the project files reside. So right here, here's our solution. And I actually don't create a folder for the project when I create my new project. So the solution folder and the project directory are actually the exact same thing. And you can tell by, all right, why are you not resizing? There we go. You can tell basically by the solution directory is where the SLN file is. The project directory is where the VCproj file are. In this case, as I said, they're both exactly the same place, and we want to go with that. So we want to keep that the same. So project directory is a good choice. So all we need to do now is come in here and create a new folder called images, and we grab our file and dump it into images. So if you look in images, there's our file. So now our pathing works. This code, close that out. This code right here should now work properly, but that's where you set your path. So if you wanted to have it, you know, debug is where your executable is ultimately generated. So if you wanted to be in the debug folder, you could have also used it. And coincidentally, there is a macro for that as well. And you can set the macro in. Let's bring the project. Oops.
Layout 90210 template. Yeah.
I actually turned on narrator. Let's turn that off. Now click here. Unfortunately, narrator is Windows key and enter, whereas show properties is Alt and enter, and I keep switching keyboards, and those two keys are swapped on the two different keyboards, so it's driving me nuts. So anyways, right here, you can also set this via edit and then macros. So you have all these different options you could go with. Or you could just come in here and quite literally put the direct path. So you could just change this to C:/ my directory is here, like so. We're going to do none of that, so let me just, oops. Alright, there's no undo. So we'll stick with the default, like so. And here's the other trick. So what we want to do is tell it where those DLLs are located. And you can get away with DLLs. You can actually copy them into your, in theory, working directory, beside the executable and debug directory, etc. But copying these DLLs every time is kind of a pain in the butt, especially if, like me, you're creating a lot of different projects. Well, there's a bit of a trick you can do. You can actually modify your environment here. An environment is basically this. And you can change it. So what I'm going to do is modify our path setting, and path is used in the DLL determining direction as part of it. And we're just going to append to our path. Now, super critical here, however, no spaces and match exactly. It's very finicky, so you need to follow this particular order. And then now what I'm going to do is just give it to the path to my SFML DLL directory. So, like so. So there's where all these DLLs are. So you can get away with it. You can configure it. So again, you don't have to do this. You could just copy those DLLs in either to your debug folder or to your system32 directory and not worry about any of this. But then if you start doing upgrades or such, you can run into some issues. You can hit DLL hell pretty easy. So this is the workaround I've been using. So okay, so now we've defined and copied in our PNG file. We've set our working directory up correctly, and our environment knows where to find the DLLs. Let's press F5, and there you go. You've just drawn your first sprite successfully on screen. Ta-da! And once again, just like what we did earlier with the primitives, so the circle or the rectangle shapes, etc., your drawable class here inherits a lot of transformable stuff, so we could rotate 90 degrees, for example, if we wished. We could scale by, I think I can do a okay, yeah, let's go. Let's double the height. Actually, let's go with half, because that's actually going to go off the window. Like so, and let's just set the position. Like so. And go ahead and run, and you will see we now have a rotated, translated sprite. Again, relative to the top left corner. And if you want to talk about origins, etc., it's all in the previous tutorial, so head on back through that. But as you see, the positioning data is all basically being inherited, so the way that you deal with positioning a sprite is the exact same as how you deal with positioning just about anything else. So that's it. That is really all that's involved in getting a sprite drawn on screen. Very, very handy. Now, something I talked about a little bit earlier on, very quickly, was that load for an image. And you've got now, if you go through the documentation, you'll see you've got SF texture, which is what we used here. A texture is basically a piece of 2D memory containing image information. There's another one called SF image, and you may be wondering yourself, why is there texture and why is there image? Well, if you went back to SFML 1.6, there wasn't. There was only image. Texture is kind of the new one, but texture is the one you're going to actually use 99.9% of the time. And the key difference between those two is where they reside. A texture resides in GPU memory, and you don't want to change textures a lot. The texture switching is an expensive process. This is why we're actually going to use a texture sheet in the next tutorial. It's an optimization trick. I'll cover that in a little bit more detail there. But loading and drawing from GPU memory is many, many, many times faster than from system memory. And system memory, this is your general purpose RAM in your computer, that's where an SF image resides. So you might wonder, why the heck would you want to have an image in memory as opposed to in GPU memory? And the reason for that is because you want to edit it. So if you have a dynamic image or you want to potentially save a screenshot out to disk, etc., you need to be in system memory as opposed to in texture memory. But you can quickly, well, not quickly, but you can move one to the other and vice versa. So now we're going to look at actually creating an image dynamically, which we will then in turn use to power our texture. All right, so I'm going to right over top of the same example here, but instead of loading from file, we'll just get rid of that part completely. Now you still need a texture because the memory does need to be copied to your video card. That's what the process of the texture does. And you still need your sprite to actually position it and draw it on screen. The drawable, the code that makes this function actually work is in sprite, not in texture. So that's all still needed, but what we're going to do, instead of loading it from disk, we're going to create an image in memory and then apply it to the texture. And let me do it. And so it'll be a bit of a contrived example, but what we're going to do is create basically a checkerboard image in memory. And first we need our image. So it's SF image, like that. And first off, let's go ahead and create it. This will allocate all the memory needed, etc. Now you'll see that the last option here, we could actually pass in a pixel buffer representation of our image. We're not going to do that in this case. We're just going to set the height and width. And what did I use? 640 by 480. So basically the same as our resolution. So that created our image. Oh, I'm going to do one other thing here too. And SF : This is actually not required because we're going to set every pixel as it is. But you can also set the default color. So right now, actually I can go ahead and use this now. So now that we're done there, we're going to go ahead and we've basically just created a black square that's 640 by 480 in size. And now let's apply it to our texture. So there we've created a texture. Now we go texture dot, instead of load from memory, we're going to load from image, and we'll pass in our image like so. And that's that. And I think I should actually be sufficiently done. Go ahead and draw this, and we should get just a black screen. There you go. Ta-da. And just to show you that it actually did something as opposed to clearing things out, now we should see a blue screen. Ta-da. Okay, so that's really all there is to it. You create your image, you load the texture from the image you've created, and you're good to go. And at the same time, coincidentally, you can also go copy to image to turn a texture back into an image if you want to go the other way. You would do that, say, for example, if you took a texture that was the screenshot, or you wanted to save something from memory to disk, etc., you could do it that way. So anyways, now we've created our image. Let's go back and create this as black again. Now let's populate it. And this is the nice thing about being in system memory as opposed to GPU memory, is we can actually update it. Now I want you to be aware of one other thing. Now system memory updates are slow. Pixel by pixel updates are really slow. So you do not want to do this inside of your game loop or anything. This is something you will not do on a per frame basis ever. But now we're going to do exactly what I said you're never going to do. And we're going to loop through every single pixel in our image, starting with, we'll go top to bottom and then left to right. So y equals 0, y is less than 480, y plus, underscore, y plus plus. Start that block off. Okay, so for every single vertical pixel, now we're going to go left to right. So let's keep my spacing consistent, int x equals 0, x less than 640, x plus plus. All right. So between these two, we just went through every pixel in our image. Now we should actually do something with it. And what I'm going to do is I'm going to set a pixel at either black or white, depending on what their position is. And then we're going to have, so we're going to need a bit toggle that's going to say are we currently drawing black? Or are we currently drawing white? And that's a bool. Is black pixel? No. Oh, now I'm going to go ahead and we could use out of the box colors, but I'm going to actually show you creating a color value in code instead. So we want color. So each thing within our image, our SF image, is a color value. Color has a 256 byte, 0 to 266 value, or 8-bit representation for red, green, blue, and in the alpha channel. We discussed this a little bit in the last tutorial. So we want a color for a black pixel and a color for a white pixel. So let's create our black pixel first. And a black pixel is no colors except for full alpha, and a white pixel is all color and full alpha. So we have a black pixel and a white pixel. And now we're going to, basically every 8 pixels, we're going to switch it up. So go from black to white to black to white, which will give us ultimately our checkerboard. That means if is black pixel, we want to draw a black pixel. If it's a white pixel, we want to draw a white pixel. And image dot set pixel. So this is how you actually set an individual pixel within the SF image itself. And that we just pass in which pixel to update. So we want our X and Y value and then the color to set. So this is for black pixels, we'll pass in black pixel. Like so. And otherwise, let's set pixel X, Y, white pixel. Like so. So basically we go through, if we're drawing black pixels, we draw a black pixel. If we're drawing a white pixel, we draw a white pixel. And now what we want to do is every 8 pixel switch between white and black. And that's simply a matter of if not X modulus 8. So if divided by 8 gives a remainder, it means that we're on the 8th update, and we'll toggle. So I think that's our right pattern right there. And we just want to flip the status here. Is black pixel equals is black pixel. So basically invert the value of that. So if it was white, it becomes black. If it was black, it becomes white. And that should basically do it. And now we want to perform basically the same logic up and down so that we draw a checkerboard as opposed to a dotted line of Morse code looking junk. So now we're just going to do the exact same logic on the vertical row. 8. Y value. I'm in the right position, I believe, and that would be it, other than my error. Missed a bracket. There. Okay. So in theory, I run this, and we shall now have an image that is a black and white checkerboard. Ta-da! So that is procedurally creating an image file. Again, you're not going to do this too often. A lot of times what you would actually end up doing is taking the texture out. So basically, as I showed you earlier, turning a texture into an image, which then you could do updates to. You could usually like add a watermark or whatever information you want. But there are sometimes you might want to do procedural generation of your texture sources. One option would be, say, pixel swapping. So if you wanted to have, blue ninja versus green ninja, etc., you could procedurally do it, create a set of images, and then copy those into textures, and you're off to the races. But that is a key thing to realize. Ultimately, if you're drawing it, it's a texture. Use a texture, it resides in GPU memory. But if you need to modify it, you move it into an image, an SF image, which then exists in basically general RAM. Can't be drawn, much slower to work with, but you have direct access to the pixels that compose it. And you can use them then to modify or create one, or like as you saw here, create one completely from scratch and copy it over. And that's pretty much all I want to cover today. In the next part, I'm going to be looking at dealing with sprite sheets, which is multiple images in the same texture. Again, it's performance-wise, it's best to not swap textures that often, so having multiple images in the same texture is definitely a good performance trick. It's also a nice logical way to store images, and at the same time, loading one file containing 32 images is a hell of a lot faster than loading 32 separate files. So it's pretty much every single 2D game under the sun uses sprite sheets or sprite atlases or whatever they want to call them in some form. So in the next tutorial, we're going to look at that specifically. So that's it. That is drawing sprites in SFML. Hope you enjoyed that. Stay tuned for the next part. See you later.